fundamentally, we've built this on the shoulders of all that have gone before. So we're using the long tried and tested method of an induced sloping ring in the wind vane, and that is sensed internally with a circuit board which has got an induction coil and two measurement coils at right angles. Now, inevitably, because the fundamental measurement is analog, no two coils are ever going to be exactly the same. As the vane goes through 360 degrees, the output of these coils is not going to be perfect. However, what we do is we put each PCB that we make is put into a test rig which is stepped around 4,800 steps to a full circle, and a lookup table is created which is then put in an EEPROM where the actual position of the elliptical sensing ring compared with the output from these coils, so that the output from this board that goes into your instrument system is calibrated to 0.2 of a degree overall. The other finer point on that is that each board is sent out with the same zero. So when you put a new board into an existing system, the zero position of your wind vane should be the same as it was before. Okay, well, we've put a huge amount of thought in the design of this wind vane to make it as fast a response and as accurate a response in terms of measuring apparent wind angle as possible. Because remember that apparent wind angle is so crucial to the instrument computation of true wind angle, which particularly upwind is really, really important. So there's a number of features in here which I'll point out. The first and most important is the high aspect ratio. So trying to keep all of the area of the vane itself as close to the axis and the counterbalance close to the axis. And that's simple physics. If you want, let's say, the counter vane to have the smallest moment of inertia, i.e. the fastest response for the same weight, you want to make it as short and therefore heavy as possible. So just to explain in simple terms, the same weight put twice as far out will give you the same half the weight put twice as far out will give you the same moment, but of course it'll have twice the moment of inertia, because moment of inertia goes up by the square of the distance, not by just the distance. The same applies then to the vane. The second thing we've done is make the whole thing as light as possible. This is a carbon vane, which again reduces the moment of inertia and speeds up the response. And then the third aspect is to keep the vane in as clear air as possible. So obviously the air flowing across this is going to be disturbed behind the boss and behind the counterweight. So you want to keep as much of the vane as possible in the clear air. And they're the three components that give this the fast and accurate response to the apparent wind angle. Okay, well, a number of general improvements. The first, most important thing is that in both at the top in the vane and the cups, these bearings, which are interchangeable with legacy systems, we put ceramic bearings in here, so that reduces stiction and friction in general. So, I mean, you put ceramic bearings in your bike, why wouldn't you put them in your wind gear? You'll get bored waiting for that to stop spinning. You really will get bored. The other thing that we've done is we've made this out of graphite loaded material. So it's very strong. On large boats, the shock loading on these is absolutely enormous and certainly strong enough to have them fly off. So these need to be built as strong as possible. But the other advantage is by loading a lot of graphite in here is that these are fully conductive. So that forms a Faraday cage around the internal electronics, which reduces the likelihood of damage when you've got static above the boat.